Hello everyone, today in this video we will be discussing the second module of operating system. In this module we have three topics. First one is multi-threaded programming, and second and the third one is about process scheduling and synchronization, which are having algorithms and some problems and solutions which are very important from exam point of view. Okay, so this is a theoretical topic and it's the shortest of these three topics. So we'll be learning about what is multi-threaded programming. Okay, till now we know what is a process, right? Process means the way of performing a task, right? Now we'll be looking what is threading. Okay, and so before beginning, if you like this video, hit the like button and don't forget to subscribe to my channel. All right, and so without wasting any more time, let's begin. So let's first understand what is threading. Okay, see, this is the process. Suppose that there is a process to add two numbers. So threads can be understood as a part of the process. Okay, so the first thread can be taking the input from the user, second thread can be storing those two values in the registers, and the third one can be calculating the result, and fourth one can be displaying. So each of these threads perform a small task. Okay, the whole process is divided into many parts, each is known as a thread. Okay, so a thread is the basic unit of a CPU utilization. Okay, so wherever the CPU is, a part of that CPU utilization will be done by each thread. Okay, and what does thread consist of? Thread has four parts. First is ID, to identify which thread it is, and PC means program counter, and stack and registers for storing the values. Okay, so by using all these values, a thread can be uniquely identified. So there are two types of threads. First one is single threading and the second one is multi-threading. In single threading, the whole process is not divided into many parts, but it's considered as a single thread. Okay, so you can consider the example of display function. Means in the screen, if you have to display, you can't divide the process of displaying into many parts. Just it's that wherever the thing is, you have to just display it. Okay, so in that case, a single thread is enough. While in the case of taking the input from the user and then calculating the result and displaying can consist of multiple threads. Okay, so each of these threads will have a separate register and stacks. Okay, but they will be sharing the same code, data and the files which is in the main CPU. Okay, so the resources are being shared, but they will have their own places like registers and stack to store their independent values. And one more thing, that the process will be independent of each other. Okay, see, in multi-threading, if there is a task to take the see, whenever you type something in the notepad, at that time whenever you enter a key value, it will be displayed here, right, in the screen. Second value you enter, that will be displayed here. Let's understand what's happening actually in this process. Firstly, a thread is assigned for taking the inputs. Second, a thread is assigned to store those inputs in the registers. Okay, so suppose that I press the key A in the keyboard, so a thread will be assigned to take that input, and another thread will be assigned to store that input in the memory, and the third thread will be assigned to take that input from the memory and show in the screen. So three threads are used, right? And what's the advantage is that even if a thread is not working in the middle, it will not stop the process of taking the input and displaying the output. Okay, so it's independent. Means, see, suppose that the memory is not working for a few amount of time. Okay, so in that case, the input will not be stopped, output will also not be stopped. Okay, the process will be going on, like the input will be coming and the output will also be happening. But in case of single thread process, if it was a single thread process, at that time whenever a person enters a key value here, that key value will be stored in the memory, that will be displayed. Till that time a user can't insert another value, but in this case the user can continuously keep on inserting the values and it will be continuously getting displayed, because it's happening due to multiple threads performing the task independently. Okay, so that's the advantage of multi-threaded programming over single thread programming. There are four major benefits of multi-threading. First one is responsiveness. Responsiveness means since there are multiple threads, it does not the fault of one thread does not stop the whole process. So the responsiveness will be the response will be carried out by the other threads. Okay, so the whole process will not stop, and the overall responsiveness will be high only. Okay. Second one is resource sharing. Since as I told you before that all the threads share the same resources, what is the benefit of sharing the same resources? By using the same resources, the multiple tasks can be performed in the same address space. Okay, that's one advantage. And economy means we need not have multiple CPUs and multiple registers and all for multi-threading. Okay, since they share the resources, it's economical. Okay. And the fourth one is scalability. Scalability means in the case that there are multiple CPUs, multi-threading can be used for, see, if there is a process here which has multiple threads, all these threads can be assigned to single CPU. Okay, or else what will happen if it was a single process? In that case, the whole process should be assigned to either of the CPUs. In that case, it will take more time. But if the task is divided into multiple threads and given to each CPU, it will perform the parallel operation and the task will be executed much faster than the traditional method. Okay. Multi-core programming is very closely related to multi-threading. Okay. In multi-core programming, there will be multiple CPUs. Okay, so that the threads will be assigned to each CPU and the work will be done very faster. Okay. But there are 5 challenges which are being faced in the multi-core chips. First one is dividing activities. It will take time to divide each activity to the multiple CPUs. Okay, so that time is also being considered here. And finding the balance. Suppose that in case one of the CPU is having very less task. At that time, other CPUs, a part of the task of the other CPUs must be assigned to this CPU so that there will be a balance. So to make the balance, CPU cycles and other resources are required. And the third one is data splitting. Means data should be shared equally among all the processes, right? And they should be able to perform that independently without interfering with each other. So that control should also be managed. And the fourth one is data dependency. Means there should be synchronization. Means suppose that there is a process here and another process here. This process is sending some data to this process, but if this process is busy with other tasks, at that time there will be no synchronization and the data sent here will be lost. So that should not happen, right? So there should be synchronization. To control synchronization, the other CPU cycles must be used here and that will cost extra usage of resources. Okay. And the last one is, it's not that much easy to test and debug the errors happening. Okay, because since there are multiple tasks happening, we don't know exactly in which task the error has happened. Okay, so that's very hard to test and debug. Okay. Coming to multi-threading models, there are 2 types. First one is user thread and second one is kernel thread. Kernel, as you know, it's closely related to CPU. User is the programmer who is developing the software. Okay, so these both have separate threads. So user's threads will be stored in the user library and the kernel will not know anything about these libraries. Okay, and the kernel will have the threads in itself which are independent of the user libraries. So these both are independent softwares, and in this kernel they will be managing of the resources which is absent in user libraries. Okay, so the similar groups of the threads will be managed, will be grouped together in the kernel, whereas in user libraries they will be taken separately. Okay, there will be no groups in user libraries. Under this, there are three types of model. First one is many to one model. Many to one model means there are multiple user threads and they are trying to access one kernel thread. In this case, only one can be processed at a time, and the second disadvantage is that when the kernel thread blocks, the whole process will be blocked here. Okay, so no process will be able to execute its thread unless the kernel unblocks its thread. Okay, that's many to one model. The second one is one-to-one model. In this model, there will be separate kernel and the user threads, so they will be executed parallelly. But the disadvantage is that it is slower because time will be taken to allocate which thread will be having which kernel. Okay, so the time is being used in allocating that resources there, so it's comparatively slower. The last one is many to many model. In this model, it's not compulsory that this thread should be assigned to this thread. The same thread can be having the tasks splitted among 3 kernels. Okay, so that's a great advantage of that. And the second advantage is that if one of the thread fails or one of the kernel fails, it does not affect the whole process. The other threads and the kernels will be still working. So many to many model is the best among all these 3. Okay. Thread libraries are nothing but what's a library? A library will have many types of books organized in a order, right? Like fiction books and scientific books and story books, all will be placed in a separate block, right? So that's what the thing is in thread libraries. Separate blocks will be made in the thread libraries which will have similar types of threads. Okay, so they provide an API for creating and managing threads. There are 3 main thread libraries in use. First one is POSIX P thread. Okay, in this library the threads will be of user type or kernel type. Okay, the second one is Win32. This is purely kernel level library, and the third one is Java threads. This is mostly most widely used library. In this, it might be kernel or the user, depends on the system. Okay, how the system is configured. If it's made for the use of kernel, it will be having kernel library, or if it's for the user, it will be having user library. Okay, so what does library look like? Suppose that calculating the sum of first n natural numbers is the task. So threads will be taking n inputs and calculating the sum and displaying the result. So these types of threads will be arranged here in multiple blocks, and the user is able to access in the POSIX form, Win32, or in the Java class. Okay, so if you are writing the code in POSIX or Win32, you'll be using C programming, or in Java if you will be having the objects and the classes by using these threads. Okay, this will be having separate threads here for each type of class. Okay, and in Win32 and POSIX, it's mostly related to assembly level language, so that will be in kernel level, and the companies developing those specific softwares will be using these two, and the companies producing the products which are used by us in our daily life will be mostly in Java. Okay, so these companies will be using Java programming, whereas these two will be using the C programming for kernel level language. Okay, but the task will be same, the threads will be assigned, the threads will be performing the same tasks, but they will be written in a different manner. Okay, let's discuss some of the major issues being faced in the threading domain. First one is fork and execute. Okay, fork means suppose that there is a process and it has to be divided into two parts. Okay, that's known as a fork. So if there are 3 threads here, which process will have how many threads? That's the problem. Some systems will duplicate all the threads, or other system will duplicate only the thread that is invoke the fork. Okay, so there's a inconsistency in fork. And the second one is execute. Execute means calling a program or a particular process to be executed. Okay, so in that case, if a thread invokes execution, at that time the program specified, this program which is specified here in the parameter to execute, will replace the entire process. So the process was to so suppose that the process was to add 2 numbers. At that time the input was taken, the program to add the 2 numbers was called. Okay, and while this program was called, at that time the whole process was replaced by this program, so that the computer won't know what was the process being called. So that's a limitation of threading. Coming to second one, which is thread cancellation. Suppose that there is a database and there are multiple threads assigned to find a keyword in the whole database. Okay, so what will happen if one of the thread finds that keyword? At that time this will stop the whole process of searching, because the key is found, right? So how will that affect the other threads? Other threads might be still searching it, but if they get suddenly terminated, it might cause problems, right? So that is thread cancellation. The third one is signal handling. Signal handling means whenever a process or whenever a process is going on, an event happens. Event can be input or the output. Means if the user enters some key value, at that time the signal happens. The signal will notify the process that it should stop its normal execution and handle the input. Okay, so at that time the signal plays a major role in stopping this process. So it's very important that the signal is handled properly. So there are 2 types of signals. First one is synchronous. In case if you have written a code of line that divide by 0, at that time it's not possible. So the normal execution of the program should stop, and it should return an error that divide by 0 is not possible. Means the signal is being sent to the same program, the program which is executing. Okay. And the second one is asynchronous. In asynchronous, the signal is sent to another program. Suppose that from the notepad I copied a text here and I pasted in Google. Okay, at that time the Control C will stop the program's execution, normal execution from notepad, and it will change the location to the Google. So signal should be handled properly, so that the copied text should not be lost in between, and it should be reaching the desired location properly. Okay, and as we know that there are 2 types of threads. First one is single threaded and second one is multi-threaded. In single threading, the signal handling is easy because there is just single thread, so that the process will return the signal to the same program. But in multi-threading there are 4 processes which might arise where the delivery should happen. Okay, you can consider the example like the delivery to the thread should happen to the single process, or to every process, or to certain threads, or to specific signal thread, or it should not deliver to the threads, but it should deliver to the other process. Those things, multiple possibilities arise. So at that time it should be handled properly to ensure that the data being sent should be sent to proper location. Okay, so that's the third threading issue, which is signal handling. The fourth one is the threading pools. What can you understand by the term thread pools? It's a pool having multiple threads. Okay, what's the need of having thread pools? Consider a case where the web server is getting multiple client requests. Okay, so it's nothing but if the multiple users are trying to access the same server, at that time since the resources are limited, each one will not get the same amount of resource, and it's also time consuming because the web has to decide which process has to be given first priority. Okay, so to overcome this, thread pools are used. In thread pools there will be fixed number of threads. Okay, and each client will be given the same thread for the same thread for its work to be done. Okay, so it's overcoming the limitation of resource limited, because the whole resource will be divided into equal parts and will be given to the each client. And it's time saving also, because the web server will not have to decide to which client it should be given. All will be given equal threads. Okay, and if the threads are finished from the thread pool, at that time the server has to wait to fulfill the request of the new client until one thread becomes free. Okay, so by implementing this, much of the time and the resources will be saved. And the fifth one is thread specific data. That means, see, as we know that threads share the data, but some threads they need their specific data only. They don't need to share the other data, because the task which they are performing, it has nothing to do with the other data. So in that case, thread specific data will be used, and each thread will be identified by a unique ID. The last one is the scheduler activation. Scheduler activation means if a user thread is accessing the kernel thread, at that time if any error is going to happen, that time the kernel should inform the user thread that an error is going to happen. So make some arrangements to not cause the loss of the data or damage of the software. Okay, so in that case a user thread can allocate other threads for the rectification of the error which is going to happen. At that time the smooth flow of the program will be happening. Okay, that's known as scheduler activation. And to facilitate the communication between the user thread and the kernel, LWP is used. That means lightweight process. Okay, this will act as an intermediary between kernel and the user. To process scheduling, what do you mean by process scheduling? Scheduling is the process of assigning tasks to CPU when one process is in waiting state. So if the CPU is here, at that time if one process is waiting for the input output operation, at that time the CPU can be assigned with other process. Okay, so that will save the time. So that performance is nothing but the scheduling of the process. CPU IO burst cycle. What do you mean by CPU IO burst cycle? In CPU IO burst cycle, the whole process is divided into the CPU part and the IO part. So suppose that load and read operation will be performed by CPU. Next is to wait for the input output, then to store the information, then wait for the input output, and then write the information. And this goes on until the last process to terminate the program, that will be done by the CPU. Okay, so this cycle is known as CPU IO burst cycle. And CPU scheduler is nothing but the program which will schedule which task to be given to the CPU when the CPU becomes idle. Okay, so there are two types. First one is non-preemptive and second one is preemptive. It's very important because it's repeated a lot of time in the upcoming topics. So understand what it is. First one, in non-preemptive, the task which is being performed by the CPU, it will get completed full, and that time only the task will change. Okay, before that new task can happen. That's non-preemptive. In preemptive, if a task is going on and it can stop in middle and let the other task execute itself, and after that gets over, it can resume its task. Okay, so that's preemptive. What is dispatcher? Suppose that there is a process selected by the scheduler to be performed by the CPU. At that time, three functions should happen. Switching the context. That means the process which is being performed by the CPU should stop and the new process should start. So that is known as switching context. And suppose consider an example of taking the input from the user and displaying the result. Okay, displaying the input. So in that case, the switching should happen from the user mode to the kernel mode. When the input is being given by the user, that's user mode. but when it's time to display, at that time the kernel mode should on, right? So that's switching from the user mode. And third one is jumping to proper location in the user program to restart that program. This means that if multiple inputs are being given by the user, at that time the input operation, see input also has a program which is getting executed each time the user inputs, okay. So whenever the input comes and the result is being displayed, after that the input program should again execute, right, for the next input. So that's nothing but the jumping to proper location in the user program to restart that program. Which program? Taking the input program, okay. So after taking the input once, it should start again from here to take the new input, okay. So that's the third point. Coming to scheduling criteria, what are the factors upon which the scheduling should happen? First one is CPU utilization. So that so the CPU must be kept as busy as possible to make the most utilization of the CPU. Second one is throughput. Throughput means the number of tasks executed in a unit amount of time, okay. That's throughput. And the process which has the throughput as more, that will be executed first, okay. And the third one is turnaround time. Turnaround time means the waiting time, like for example, to get the information from the memory and from the ready queue, and to execute the program and to take the input output, okay. So that's the turnaround time. For maximum utilization, the waiting time should be as less as possible, okay. And the waiting time and the response time are the times which is spent in waiting, and the response time is the time taken to start responding from the submission of a request. So suppose that the user has entered some value and the value is getting displayed in the screen. The time taken to display the value from the time of the input is nothing but the response time. That means after giving the input, how much time the system takes to respond to that input, okay. That's the response time. Coming to scheduling algorithms, it's very important that you understand what is ready queue, okay. This is the CPU here, and the ready queue will have the tasks which are to be executed, okay. So the scheduler will take up any of these tasks and assign it to CPU. So which of the tasks should be taken, that is decided by the scheduling algorithm. There are 4 or 5 types, and it's very important from exam point of view, okay. So listen very carefully to whatever I explain, okay. So the first one is FCFS, which means first come first serve. So suppose that there are tasks which are P1, P2, P3, okay, and they take time as 24 millisecond, 3 and 3 millisecond, okay. So they come in the CPU in the order P1, P2, then P3, okay. So how much time will be taken for each task to be executed, okay. So if P1 comes first, at that time 24 seconds the P2 and P3 have to wait, and P2 have to wait 24 seconds and P3 have to wait 24 plus 3 27 seconds, okay. So average time will be 0 plus 24 plus 27 divided by 3, okay. So each task will have approximate waiting time as 17 milliseconds. So basically what we are doing is, in each algorithm we will be calculating what is the average waiting time for each process, and then we will be finding out the best algorithm. And it's not that one algorithm is the best one, so according to different situations, different algorithms will perform better, okay. In this case, how can we make the average waiting time lesser? See here, if we take this order, if we take P2 first, then P3, then P1, what will be the waiting time? See, if we take P2 first, 3 milliseconds, P2 will be over, then after 3 milliseconds P3 will also be over, at last P1 will take 30 milliseconds till 30 milliseconds, okay. But the waiting time, see here how much it is. For P2 there is no waiting time because it's starting from 0, so 0 here, and after it gets over, P3 is starting, right. So 3 milliseconds for P3, and for P1 it is 6 milliseconds because P2 and P3 took 3 milliseconds respectively, okay. So P1 will have 6 milliseconds here, so if you divide it by 3, you will get 3 milliseconds. It's far less than the previous one, which is 17 milliseconds, okay. So in that way we are finding out which is the best way to which is the best order to set the process so that the average waiting time will be less, okay. Observe here that the total time taken is 30 in both cases, but in this case the average waiting time is far less than the previous one, okay. The second one is shortest job first scheduling, okay. That means if there are multiple tasks here which are taking different amounts of time, the task which is taking the least amount of time will be executed first, then the second least amount of time. Like that we are executing all the tasks, okay. And in this algorithm there are two types. First one is non-preemptive and second one is preemptive. So let's see what's the difference between both. In non-preemptive, the current process is allowed to finish its CPU burst. That means if a task is going on, other task can't come in middle. Okay, so when this task gets over, at that time only other task can execute. Okay. And the second one is preemptive. In preemptive, if this task is going on and if the other task is taking lesser time than the remaining time of this task, at that time this will be executed and this task will be paused. Okay, so that I will be explaining you by an example. Okay, so see here, suppose that these are the process taking this amount of times, and for non-preemptive the least time, see which is the least time, this is the least time, so P4 is placed first, second least time is this one, P1 is placed second, then the third one is P3, then P2. Okay, so in this way non-preemptive SJF is executed. Calculating the average time we get as 7 milliseconds. Okay, let's see what's the case in preemptive. In preemptive, a third column will be taken into consideration, which is arrival time. What does arrival time mean? See, P1 will arrive at 0 millisecond, means at the starting point P1 will be starting here, okay, at 0 millisecond, and P2 will arrive at 1 millisecond. So see here, this is the time graph. At 0 millisecond P1 is going on, and after 1 millisecond P2 came. So at that time it will be decided whether P2 should be given priority or P1 should continue. So let's see the time here. See P1 takes 8 milliseconds and P2 takes 4 milliseconds. After 1 millisecond P1 will take 7 milliseconds, right, when P2 comes. At that time it will be compared if 4 is less than 7 or not. If 4 is less than 7, at that time P2 will be given the priority, and P1's execution will be paused for a while. Okay, so after that when P2 comes here, P2 will be executed from 1 millisecond to 5 millisecond because it takes 4 milliseconds. P1 was stopped because initially it was 8 milliseconds, then after 1 millisecond it was 7 and P2 came. P2 has 4 milliseconds total time of execution and P1 has 7 milliseconds left. So P2 is lesser, right? So P2 is getting executed in the next 4 milliseconds. Then at the same time when P2 was getting executed from 1 to 5 millisecond, in between P3 and P4 also came. They both also were compared with P2, which is 9 and 5, and as we know 4 is less than 9 and 5, so P2 was continuing its execution. After that P2 got over at 5 milliseconds. At that time we will be comparing which is the lesser. See, P1 is 7 now and P3 is 9 and P4 is 5. Which one will be taken into consideration? P4, right? It's the least one among all these three. So P4 will be executed for the next 5 milliseconds. See, P4 will be executed from 5 to 10 milliseconds. After that, after P4 gets over, 2 are left, which is P1 and P3. In this case, which one will be taken? 7. So P1 will resume its execution from 10 to 17 milliseconds. At last P3 is left, which will execute from 17 to 26 milliseconds. So let's calculate the average time taken now. See, for each process we will be calculating separate. First one, when P1 resumed, it resumed at 10 milliseconds, and before that 1 millisecond was already given to P1. So total time waiting for P1 is 9 milliseconds. So that will be written here, 10 minus 1, which is 9. Then waiting time for P2. P2 had no waiting time because when it came here, P1's time was more, so P2's execution started at the same time. Okay, so P2's waiting time is 0 millisecond. Then P3's waiting time. P3 waited till 17 millisecond, but when it arrived at 2 millisecond, right? So waiting time is 17 minus 2, which is 15 milliseconds. Okay, and the last one, which is P4. When P4 came at 3 millisecond, and when it got started its execution, it is at 5 milliseconds. So it waited for 2 millisecond, which is 5 minus 3, and calculating the average we will get as 6.5 millisecond. Okay, so it's better than the previous one, which is 7 millisecond. So in this case, preemptive will be better for this problem. Okay, and the third one is priority scheduling. That means there will be priorities assigned to the task, and it will be executed according to the priorities. Okay, so suppose that these are the priorities here, and according to these priorities it will be given the execution order. Okay, the first priority is given to P2. Okay, so P2 will have the first execution at 0 millisecond, and P2 takes how much time? It takes 1 millisecond, right? So it will perform the task till 1 millisecond, and after that second priority, which is P5, it will perform the task for 5 milliseconds, and then it will change the execution to P1. Okay, so like that all the tasks will be performing their executions based on the priorities. Okay. The fourth one is the round robin scheduling. In round robin scheduling, the queue will be first come first serve, and in this case it will not be the normal queue, but there will be time slicing. Okay, so for each process a particular amount of time will be given, and when that time gets over, the next task will be given the particular amount of time. So let's see an example here, which is first P1 will be given 4 milliseconds. Okay, and after the 4 millisecond gets over, then P2 will be given 4 millisecond, but P2's execution time is just 3, so after 3 seconds it will be over and the time will be given for P3. P3 is also 3, so it will be getting over within 3 milliseconds, and then P1 will be resumed. P1 will be given 4 milliseconds each intervals till the P1 gets over. In this way, average waiting time is calculated, means total time spent waiting divided by how many processes were there. Okay, in this case we get 5.66 milliseconds. In multi-level queue scheduling, the whole queue will be divided into many parts which will have its own algorithms and the priority levels. Okay, and the last one is multi-level feedback queue scheduling. In this, the feedback is also taken, means if there is a process which is taking which is waiting for a long amount of time, its priority will be increased, or there is a process which uses too much CPU time, at that time its priority will be decreased. So in that way, the multi-level will change its priorities according to the type of process. Okay, till now we had discussed about a single CPU having the multi-threads. Okay, that's known as multi-thread programming. But in this case, if there are multiple processes, means there are multiple CPUs, the task of scheduling becomes more complex. So there are a few ways to overcome the difficulties faced by the users. Okay, so first one is approaches to the multiple processor scheduling. So first one needs to decide that in what way the scheduling will be done. Either it's asymmetric or symmetric. In asymmetric, there will be a master which is responsible for all the scheduling decisions, and in the second one, symmetric, each processor will have its own self-scheduling process to examine the ready queue and select a process. Okay, that's known as symmetric. That's known as symmetric multiprocessing. The second one is processor affinity. To understand this, consider an example here. See, this is the process, this is the processor, and this is the cache. So when a process is getting executed, at that time the mostly accessed data will be stored in cache, so that the processor will easily access the data very faster. But sometimes the process needs to change. Okay, at that time the processor should change from one location to other location. At that time the cache will also change. So it will be very difficult for the new processor to get the data very quickly, because this cache won't know what type of data the processor was already accessing to. Okay, and it's very costly to transfer this whole data of this cache to the new cache. So to overcome this, one thing can be done. The process should try its maximum to not change its processor. That's nothing but the processor affinity. The third one is load balancing. In this, the server have to decide which process is having the more data, so that the balance will be made from the more data to the process having the less data. Okay, that should be done by the server. To handle multi-threading effectively in multiprocess, what can be done is the creation of logical CPU. So within a single CPU, there can be multiple logical CPUs, which can facilitate the performance of multiple processes in a single CPU. Okay, by dividing those CPUs into multiple parts. Thread scheduling is nothing but the setting of the user threads to the respective kernel threads. Okay, for that, two processes are used. For the user threads, process contention scope is used, and for the system threads, for the kernel threads, system contention scope is used. Okay, so in this, by using these two processes, appropriate user and the kernel thread is selected, and the connection is made between them. Okay, there is a second way to do it, which is similar to it, which is called p-thread scheduling. In this, the difference is that it uses two functions, which is for getting and setting the contention scope policy. Okay, so it's a bit better than the previous one and more reliable. Okay, what does process synchronization mean? Process synchronization means to maintain the data consistency, the orderly execution of the process is necessary. So suppose that there is a producer here and a consumer here. Okay, so a producer should produce the data how much the consumer can consume. If it produces more data than what the consumer can consume, then for some amount of time the data which is being produced and not consumed by the consumer will be lost, right? And the opposite is also true, where the consumer is trying to consume data which is not yet available in the buffer. Okay, so in that case the time will be wasted in checking if the data is available or not. So there should be a synchronization between the producer and the consumer, so that effective utilization of the resources will take place. To illustrate this with an example, consider an example of producer consumer problem. In this we will be using a counter which is initialized as 0, and whenever the producer produces a new item, at that time counter will increase, means it will become 1, and whenever a consumer consumes the data produced, that at that time the counter will become 0. Okay, and the order in which the product is produced and the consumer is consuming the data, and again the product is produced and the consumer is consuming the data, or 2 times the product is produced or 3 times the consumer is consuming the data, the order in which these things happen is nothing but the race condition. Okay, I'll be giving you an example and explaining you what race condition is. See, before that, understand how the implementation of counter plus is. In counter plus, what we will do, first see if the producer produced a data, okay, P naught, at that time register 1 will become counter. If the counter is initialized as 0, register 1 will have the value 0, and register 1 will increase its value by 1. Okay, so register 1 plus 1, now register 1 has the value 1, and that value will be copied back to counter. Okay, so this is a 3-step process. In first step, the register 1 will have the value of counter, register 1 will be incremented, and finally the value of the register 1 will be copied to counter. Okay, similar is the case for counter minus. In counter minus, this value will be stored in register 2 and it will be decremented, and that decremented value will be copied back to counter. Okay, so since it's a 3-step process, but the producer and the consumer will have just 1-step execution, that time the problem can happen. See, observe here carefully what happens here. Initially the counter value is 5. Okay, I have written the expected values of the counter and what actual value it is. Okay, see here, first when the producer produces some data, at that time counter should go to, means counter's value should be sent to R1. See here, whenever a producer is producing the data, counter's value should be gone to R1, register 1. So what will register 1 have? It will have 5, right? Then in the next step, again a producer produces a new item. At that time the second instruction will execute and register 1 will increment its value. So register 1 will have the value 6. Okay, and then after that consumer consumes a value. Okay, so what will be the first step in if the consumer consumes a value? At that time register 2 will have the value of counter. See, counter is still 5 only, because only register 1 has got the value and incremented. These 2 steps only have been executed. The third step is still remaining. But before this gets executed, the consumer is consuming the value. Okay, so it's not in synchronized manner, since consumer is consuming a value before the counter is getting incremented. So at that time problem can happen. Counter's value, which is actually it had to be 7, because 2 times the producer produced, but still due to lack of synchronization, counter's value is still 5. So R2 will get the value as 5. Okay, the previous counter's value. In the next execution, the consumer will consume another value. That means the counter value should have become 6, right? See, 2 times the producer produced the value, it became 7, and then consumer consumed the value, again it consumed the value. So it should have become 5. But what happens when consumer consumes the value? See here, the next step will be executed. Register 2 will become register 2 minus 1, which is 4. Okay, so R2 will have 4 now. In the fourth iteration, if producer produces a value, at that time this execution will happen. Counter is equal to register 1. At that time register 1 value, which is 6, that will be copied to C1. So C1 will be 6 now, and in the next step when consumer consumes a value, C will become R2. See, this is from the previous one. Okay, the value of the register 2 will be copied to counter. So what was the value of register 2? It was 4. So 4 will be copied to C. But if you look actually, how many times the producer produced the value? 1, 2, 3. So counter was 5, it should become 8, right? 5, it should become 8, and consumer consumed the value 3 times. So it should become minus 3. Okay, so it has made no difference, because 3 times it was produced and 3 times it was consumed. So the counter should be 5 only, right? But see, we are getting a mismatch here, which is 4. Okay, this is because of lack of synchronization and delay in the updation of the counter value. Okay, so this is nothing but the race condition. Coming to critical section problem. Critical section is a segment of code in which a process may be changing the common variables, updating a table, or writing a value. Okay, so suppose that there is a code here. Okay, the process is made up of 4 parts. First one is entry section, and in the entry section it is checked whether the process, what the process is being performed is allowed to perform or not. In the second one, the critical section, where the actual code is written and the actual updation of the value or the writing of that values will happen. Okay, and the third one is exit section. After the critical section gets over, it will come to exit section, and then the remaining section will have the remaining, if any code is to be executed, that will be done here. Okay, so this is the structure of a process. So since there are multiple processes going on at the same time, there is a critical problem that at one time only one of the process should be able to execute its critical section, or else if multiple try to execute its critical section, at that time errors can happen. So critical section is an important part of the code, so at one time only one process should be allowed. To overcome this problem, many solutions are being proposed by the computer researchers, such as the Peterson solution. So before moving on to that, we will have to keep 3 things in mind if you want to find a solution to it. First one is mutual exclusion. The solution which you provide should be able to satisfy the first requirement, which is mutual exclusion. This means that the solution will make sure that no process will be allowed to enter if one process is already getting executed. Okay, and the second one is progress. So suppose that there are multiple processes here. Okay, and all these processes have to execute a critical section in this code. Okay, now see, it's not necessary that all the code have to execute, all the process have to execute. Suppose that these 2 processes do not have to execute the critical section, only these 2 have to execute. So in that case, the competition will be only between these both processes. These both need not be involved in the competition, and that will waste the resources and the time cycles. Okay, so that's the second point, where how many actually want to get executed, that the competition should be in between that only. Okay, so that should be kept in mind. And the third one is bounded waiting. Any requested process must not be made to wait for more than a limit. Okay, so if a process is waiting for more than a particular amount of time, that should not happen, and it should be given the priority and the chance to get executed. Okay, so keeping these 3 requirements in mind, the first solution which is proposed is Peterson solution. It's a software based solution, and by using the Peterson solution, the 3 requirements are satisfied, which is mutual exclusion, progress, and bounded waiting. Okay, these are the 3 requirements which are satisfied by the Peterson solution. Let's see how it is in the execution part. Okay, so the structure of the process will be as follows. We'll be using 2 things. First one is turn. This is a variable to save some value. Okay, turn is a variable, and another will be using an array of flag. Okay, so flag will have 2 values if 2 process wants to execute, 3 values if 3 process, or n number of values if n number of processes want to execute. Okay, so 2 things are here, turn and flag. Now let's see how it works. Suppose that process P1 has to execute. At that time, the flag of 1 will become true and turn will become j. Okay, so turn of P1 will be activated. At that time, the while loop will come, and if flag of j is equal to true, means P1's flag is true, and turn is equal to j, means P1's turn is true. At that time, the critical section should be executed. Till the critical section of P1 is getting executed, flag of P1 will be true. Okay, after this gets over, flag of P1 will become false, so that next process will be able to execute its code. Okay, so in that way, after one process gets over, that time only the second process can start. Okay, so by this method, the critical section problem can be solved. Okay, the previous one was the software solution. Coming to hardware solution for critical section problem, we can use a lock and release section. In this, if a process enters a execution, at that time the process will be logged, and until the process gets over by that execution, the lock will not be released, and after it gets over, the lock will be released. Okay, so in that case only one process can perform the task at a time. Okay, so there are two ways to achieve this. First one is test and set, second is swap. In test and set we will be using a function which is bool test and set. Bool will have either the true or false. So whenever a target is there, means which process wants to execute its value, at that time it is tested if it's the true value, and it is logged. Okay, after implementation it is released. Okay, so this is the code here. First it will be logged here, target is equal to true, and then after the critical section lock will become false, so that next process can be used for execution. Okay, the second one is swap. In swap we will be using two variables, key and lock. Okay, so what happens here is a process will have a key and a lock, and these two variables will be shared among all the process. Okay, so whenever a process wants to execute its value, at that time key will become true. Okay, key will become true and the critical section will be executed, and after that gets over, key will be swapped with lock. So whatever be the value of key, that will be passed to lock, and lock's value will be passed to key. Okay, lock can be set as true or false initially, and after it gets over, lock will become false. So what happens is key will become false here, and the process will be able to end its execution, and the new process can come here. Okay, and whenever the new process comes, key will become true, and this repeats until all the process gets its values executed. Okay, Semaphore is nothing but a variable, and its value can't be directly changed. To change the value of this variable, we have to use two functions, which is wait and signal. Wait will decrease the value and signal will increase the value. Now let's see how using semaphores we can solve the problem of critical section. Before that, keep two things in mind. The functions of wait and signal is similar to lock and unlock. Okay, if you use wait, at that time the process will be locked and no more process can come, and when that process executes signal, at that time the lock will be released. Okay, so the next process can be executed. Let's consider an example here where P1, P2 till Pn are the process that wants to be executed in the critical section. And remember that all these processes share the same variable. Okay, there is only one variable of semaphore, and all these processes share the same value. Okay, now see where the code starts from. Initially wait s will be called. Okay, so suppose that first the value of s is 1. Okay, when wait s will be called, what will happen? In wait s, while s is less than or equal to 0, what's the value of s? S is we have taken as 1. Is 1 less than or equal to 0? No, it's not true, so this will not be executed, and s value will become s minus 1. So what's the value of s now? S has become 1 minus 1, which is 0. So now s value is 0. Okay, so suppose that the first process P1 came and s value was here, s value was 1. When it came and executed the wait function, at that time s value became 0 and it went in the critical section. Okay, now see, if another process wants to come at the same time, that should not happen. So how does this algorithm solve this problem? Suppose that P2 wants to come here, P2 will also execute the wait function. Okay, so s value is 0, P2 wants to execute it. Okay, so P2 came here and s value is 0. Okay, so while s is less than or equal to 0, it is having no body of the function, it's just semicolon. So what will happen? This will become true and it will keep on getting looped infinitely in this same loop. Okay, so P2 will be stuck here. Okay, it will not come out of the loop, so that is waiting time for P2. Okay, till when it will not come out? Till this statement is true. What is this statement? While s is less than or equal to 0. So until the value of s changes and becomes greater than 0, till that time P2 will be waiting in this loop. Okay, so in that way the requirement that only one process should execute at a time is satisfied by using this function. Okay, now how can P2 execute its function? P2 should be able to execute only when P1. So when P1 gets over with its critical section, at that time P1 will call signal function. What will signal function do? See here, signal function will make the value of s as s plus 1. So s was 0, s will become 1 now, and when s becomes 1, this will be true and this will become false, right? So when this becomes false, P2 will be able to enter the loop. Okay, so this becomes false, s value will again reduce to 0 and P2 will be able to go to critical section. Okay, so see here, P2 was waiting here and when P1 made signal S, S value changed to 1, and since S value changed to 1, the while loop became false and P2 is able to come to critical section. Okay, and when P2 came to critical section, S value became 0. So if any more process come here, they have to wait here. Okay, so in that way only one process is able to execute at a time. Okay, so that's the use of semaphores, and it has 3 wide applications, and we'll be looking at that. But before that, let's look at what is busy waiting concept. Okay, so as we saw previously, if a process has to wait, it has to execute the while function. While S is less than or equal to 0. So at that time CPU cycles will be wasted, right? See, suppose that the process P2 was here and it is simply executing the while function again and again. So it's wasting a lot of CPU cycles. CPU cycles can be used by other process to use for more productive use, right? So this should be avoided. So to avoid that, there can be 2 functions implemented using block and wake up. So what will happen if a process comes to wait? At that time it will not execute the while function, but it will execute the block function. What it will do? It will block the process which came here. Okay, so it will not be executing the while function, but it will be blocked. Okay, so it will save a lot of CPU cycles needed for executing the while function. And then when the signal becomes true, means gets its critical section over, at that time the signal will become true and it will call the function wake up. What will wake up to? It will unlock the block process. Okay, so that the next process can be executed. Let's understand what is deadlock and starvation by an example. See here, consider 2 processes P0 and P1 having 2 semaphores S and Q, which is initialized as 1. As we saw previously that a process P2 can't enter the loop unless P1 executes the signal also. See, suppose that P1 came and it executed the function wait. At that time S became 0, and unless P1 executes signal, till then S value will not change, S will be 0 only, right? So unless P1 will not execute this function, P2 can't enter the loop. So suppose that we are using 2 semaphores and 2 processes. In this case, waitS and waitQ are executed by both of these functions, and both are waiting for each other. P1 is waiting that P0 will execute signal S so that it will continue after this, and P0 is waiting for P1 to execute signal Q so that it will move on with this. Okay, so both are waiting for each other, and these 2 functions will never be executed, and this situation is known as deadlock. The second one is starvation. In starvation, if you use a stack here, a new process will come. If it has shorter amount of time, it will be executed, and then this will come and this will be executed, and before the next execution happens, a new process comes which is having shorter amount of time, so that will be executed. So in that way, a new process will be keep on executing, and the older process will be remaining there only. Okay, waiting indefinitely within the semaphore. So this condition is known as starvation. Classical problems of synchronization, there are 3 types. First one is bounded buffer problem, also known as producer consumer problem. In this, as already discussed previously, that when a producer produces items more than the speed of the consumer consuming the products, at that time the buffer will become full, and if it tries to produce more, the data will be lost. Okay, so to avoid this problem, what can be used is wait and signal. Okay, so what can happen if the buffer becomes full? The producer has to wait. The same is true for the opposite side also. If the consumer is consuming the data more faster than the producer, at that time the consumer has to wait if the buffer becomes empty. Okay, so in that case it will save the CPU cycles needed for checking if the buffer has the data values or not. Okay. Second one is reader writer problem. In reader writer problem, suppose that these are text here and some things are written here, and there are many people who are either reader or writer. So if they all are reader, it's no problem because all can read the text in the different speeds. Okay, so that's not a matter. If there are multiple people who are readers as well as writers, at that time, if the reader is reading these values, okay, so that reader reaches this point, at that time if a writer wants to change some value here, at that time the writer changes the value and the reader continues to read and it misses out the update. Okay, so in that case data can be lost here. So to avoid this problem, what can be used is, when a writer is writing the value, reader should not be allowed to read the document. Okay, after the writer finishes its task, at that time only reader should be allowed to access the document. Okay, so in that way the updates will not be missed by the readers. Also, two writers can't write at the same time. If one writer is writing the task, if one writer is writing the document, at that time the next waiter should wait until the first writer task is over. Okay, this can be achieved easily by using wait and signal functions. The third one is the dining philosophers problem. So consider an example here. All these philosophers are sitting in the table and they can either think or eat. Okay, and these are the chopsticks, and in between there's a bowl of rice here. Okay, so if a philosopher wants to eat, he should pick up left chopstick first and then the right chopstick, and then he can eat. Okay, so if all the philosophers wants to eat at the same time, that can't happen, because see here, if this philosopher wants to eat, he will grab the left one and the right one. So these both can't be able to eat at the same time, because they also need the left one and this needs the right one. Okay, so in this case only two of the philosophers can eat at the same time. Okay, either P2 and P5 or P2 and P4 are the opposite ones. Okay, so at a time among the 5 philosophers only 2 can eat. So by using this same analogy, what can be understood is, the philosophers are nothing but the process in the computer system, and these are the shared data values. Okay, so that data value can be accessed at most by 2 processors at a time. Okay, all the processors can't access the same values at the same time. Okay, so how can this be achieved? This can be achieved by using semaphores, in which we can use the wait and the signal function. By using wait, the philosophers has to take the chopstick. See here, when the philosopher takes a chopstick, he has to execute the wait function, so that the other philosopher has to wait for the chopstick to be released. Okay, when the chopstick use is over, the processor has to execute the signal function, so that the chopstick is free to be used by the other philosopher. Okay, in this way it will ensure that only 2 processes can be executed at a time. Okay, coming to monitors, is the same as the previous one, which is semaphores, but here we will be having the procedures also. Suppose that there is a process one which wants to access the value A. In the previous one we can directly access the value of A, but in this case we will be using procedures to access the values. Okay, so in that case why we are using is, it saves the interchange of wait and signal or the faulty calling. Okay, for the safety purpose and the ensurement of proper calling of the functions, we are using a set of procedures. And the dining problem can also be solved by using the monitors, by using the functions pickup and put down. Whenever the processor wants to perform a operation, at that time pickup should be called, and after it gets over with that, it should call the put down operation. Okay,